Part 2 of our lecture, which looks at inventory management, we will take a look at the question of how much to order. And so we have our order quantity queue, and it depends on the scenario. We will use a couple of different models. The basic economic order quantity model is where we will start. That model has been around for quite some time, and you could have encountered it in accounting, cost accounting, that is. But certainly it's a very standard model that you'll find in any operations management course. The production order quantity model, as I mentioned, is in a situation where we have simultaneous production and usage. So if we're producing a component that will be used in an assembly process later on, then that we produce that subassembly, and that's the production part of it. And then when it's used in the assembly process, then that's the consumption part of it. The quantity discount model occurs when a manufacturer or supplier is offering different prices depending on the quantity that you order. And that's often necessary of interest to the supplier because they're trying to often get some economies of scale. So the discount that they're willing to offer you would be offset by the benefits that they generate from having to produce larger order quantities and so forth. So let's examine the basic EOQ model. There are a couple of assumptions. One is that we know what the demand is and it's constant, it doesn't vary. That there's a lead time that is known and is fixed. So in other words, it is not time varying. If it takes 2 weeks to receive the item, it's always 2 weeks. The receipt of inventory is instantaneous and complete. So when you receive an order quantity, as soon as you receive it, it's not received gradually. The 500 items, if that's what you ordered, is received and you have it right away to put into your inventory. Quantity discounts in the basic EOQ model are not considered at this point. And then the only variable costs are what they call the ordering costs or setup costs and the holding costs. And then for now, I will assume that because demand is known and lead time is known and those things don't vary, that there's really no need for a stock out, because stockouts really come from situations where there's uncertainty. So we just want to sort of demonstrate how would we use the inventory over time. So if we start off with a quantity queue, over time we will use it at a constant rate depending on what the demand rate is. And so if we say, for example, our order quantity is 100 and we use 10 units per day, then if we're using at a constant rate of 10 units per day, that's our demand, then this period right here over time would be 10 days. And so therefore our cycle time is 10 days. Every 10 days we would consume the order quantity, which is 100 units. All right? And so this just sort of continues over and over again. So we receive items here, and as we receive it, we use it at the same rate. We receive the 100 items and we use it at the same rate. And so this is what we have, this sort of sawtooth diagram, which sort of shows how our inventory starts off at Q, gets used down to 0, gets to Q again, used down to 0, and so forth. But of course, we now need to place an order for the item. The orders would then arrive. We would have what we call a reorder point, where when the inventory level drops down to a certain level, we would place the order, and then the order would actually arrive here. So if we knew the lead time, for example, was 3 days, we work backwards 3 days, and that's when we should place the order. If this is 3 days from this point where the order would be received, then we place the order at this point, and if we go to this line, it will tell us that's what our inventory level would be when we place the order, and that's called our reorder point. All right. The other thing we want to look at is that the average amount of inventory is Q over 2. And if you think about it, if we consider this as a single cycle, right, then the area of the rectangle is Q, the height, times 1, which is the size of the base. You know, the area of a rectangle is just the base multiplied by the height, or the length times the width. But if you notice, the inventory is really half of that shape. In other words, it's a triangle, which is half of the rectangle. So how do we get half of that area? It would be Q multiplied by a half of the base. In this case, Q multiplied by a half. But since we're going to use our base as a unit cycle, meaning that we'll just call it a unit length, whatever that is in days. So our average inventory is basically Q over 2. In other words, this is the inventory that we keep on hand on average, right? Another way to think about it is that if you started off with Q and ended up with 0, then Q plus 0 over 2 gives you an average. That's how we take an average of the beginning and the end. And so then that gives us Q over 2 as our average inventory level in each cycle. So the investment cost that we will incur is on the average demand, not the maximum demand or the minimum demand, but the average demand. So Q plus 0 over 2, or if you just think of this as half of the size of the rectangle, base times height, or width times length. But we're only using, we see the shaded area represents half of the rectangle. All right. So we want to be able to now decide the value of Q so that we minimize the annual cost associated with inventory. And we can do that if we could just capture all the costs. So we know the holding cost is the cost on the average inventory. That's just a straight line cost. The order cost, if we have a fixed order cost, the more items we order for that fixed cost, then our cost per unit actually decreases. All right. So we'll see that actually dropping right here. And then if we add up those two things together, we have a total cost curve. And because we want to minimize costs, we know that the minimum of the curve occurs where the gradient is 0. If you remember that from your calculus, those of you who did calculus. So therefore, right around here is the minimum of that total cost curve, as you can see here. So our minimum cost would be whatever this value turns out to be, and our optimum order quantity is Q star, which is whatever the value of Q is that lines up with this point. And it actually occurs at the intersection of those two things. Okay? So we could actually represent this mathematically without difficulty. So if we decide Q is the number of pieces that we need to order, the number of items, Q star is the optimal value. So we let D be the annual units, the demand, S be the setup or ordering cost, and H be the holding cost per unit for a year. So let's say if we say, it's going to cost us $2 per year to hold this item. Or sometimes we may express the holding cost as in terms of the interest rate. So if we know the cost of the item and we know the interest rate, we'll say, well, if the item costs $10 and we're paying a 10% interest rate per year, so 10% of $10 would be $1 per year. That's what this would cost. So we could express the holding cost in terms of an interest rate and the cost of the item. Okay? But remember that the holding cost also includes some other items as well, such as insurance, storage, rentals, and all that sort of stuff. So the annual setup cost is just the number of orders that we place per year times the cost of a setup or order. And so how many orders do we place per year? It would be the annual demand divided by the number of units we order. So if our annual demand is 1,000 and we order 100 each time, then we would have had 10 orders per year. So if we multiply that by the order cost, we would get the annual order or setup cost. So D over Q gives you your number of orders multiplied by S, and then that gives you the order cost. All right? So that's what that is. Now let's look at our holding costs. The holding cost is the cost on the average inventory. Remember we said each cycle our average inventory would be Q over 2. We start off with Q, we end up with 0, so Q plus 0, and if we take the average of those two numbers divided by 2, we get Q over 2. So Q over 2 multiplied by H, the unit cost, and that gives us our holding cost. If we add those two together, we get the total annual cost. It turns out that the optimum order quantity is found when those two things, when the order cost and the holding costs are actually equal to each other at the intersection, as I mentioned to you. So if we solve for Q by simply multiplying both sides by Q and then solving for Q star, we will get Q is equal to the square root of 2 times D times S divided by H, the holding cost. And that's easy to show mathematically. We could actually do calculus where we differentiate the function and all that stuff, but it's not necessary. So here's a simple example that shows the EOQ is fairly straightforward. 1,000 units, the setup cost is $10, 50 cents per year for an item. If we multiply 2 times D, D is 1,000, times S, 10, divided by the 50 cents, which is your holding cost, take the square root of that. We will order each time 200 units. And we could substitute this 200 units in the total cost function to find out what it's actually going to cost us per year. All right? So the number of orders per year would be D over Q star. It would be 1,000 divided by 200. So that's your 5 orders per year. That's how many times you're going to order. The average inventory would just be essentially your 200 divided by 2, which would be 100 units on average inventory. The time between the orders. So if we go into order, for example, we said 5 times per year. Then if we were to take a year and divide that up by 5, then we get a sense of how long between the orders. So how many days do we have per year? We say we have 250 days. So if we go into order 5 times in 250 days, then 250 divided by 5 means we will place an order every 50 days. That's what T represents, the time between the orders. Alright? And that's fairly straightforward. The annual cost, as I mentioned, is just a matter of adding those up. So once we add that up, it will turn out that our annual inventory investment is $100 if we're trying to meet the demand for 1,000 units over the year. And if we order according to that cycle, then that is what will be our inventory cost. Now, the EOQ model is considered a very robust model, and the reason why it's considered robust is because if you look at where the optimum order quantity is, the curve is fairly flat. And because the curve is fairly flat in that region, it means that you could vary the order quantity without varying the total cost very much. And so, as a result of that, there's a range that you could change your order quantity level to that does not impact your costs very significantly. Alright? This is just another example that showed that if we were to change the total demand, then with the same order quantity, the total annual cost increases by 25%, 125. But what we could do is we could actually change the quantity to 250 units for the same annual demand and find that the cost does not change significantly at all. Okay, so this is just showing what if we determine what the order quantity would have been for 1,500 units. The optimal order quantity is really 244.9 units, which is different from 244 units. 244.9, which was different from the 200 units that we were using a bit earlier. Okay, and we see that the cost is really not a whole lot different. So what we're showing here is with the demand being 1,500 units, if we had ordered 200 units, all right, every time, the cost was $125. But if we now turn around and determine what the optimum quantity is not 200, it's actually 244.9 or 245 units. The optimum cost for 245 units is $122. What's the difference between $122 and $125? Only about 2%. And so we see here that by changing the order quantity from 200 to 245, 45 more units, that your annual cost is not affected by more than 2%. All right. Let's answer the question of reorder point. This one is has to do with when do we place the order. So we know how much we want to order, but when do we place the order? And the reorder point is essentially an inventory level that tells you when to place your order. So if you started off with Q units, let's say Q in this case was 200, you monitor the inventory level, and at some point it gets down to a value. You say, hey, we have 50 units left, let's place an order now. Now, how do you determine that? It depends on your lead time, because what you want to do is when you're placing the order and you're waiting for it, during that period you are consuming your inventory. So you want to make sure you have enough inventory during the lead time to cover you while you're waiting for your order to arrive. And so therefore the reorder point would be the inventory level that is necessary to cover you during the lead time. So if you know your consumption rate and you know how long your lead time is, then it's easy to compute what your reorder point is. Remember, the reorder point is just an inventory level. So look here, we have an example. What is our demand per day? And what is our lead time in days? So if we multiply those two, that is our reorder point. That tells us how much inventory we should have. So let's say the lead time is 5 days and we are consuming at 50 units per day. So 50 by 5 is 250 units. So we would have to have 250 units in stock to cover us for the 5-day lead time that we will incur. All right? And that is our reorder point. So when we get down to 250 units, you place that order. You have the 5 days that will be covered by 50 units per day. And then when the order arrives, then your inventory gets replenished. When it gets back down now again to 250 units, you place the next order and the cycle repeats itself. All right? And that's a fairly straightforward kind of a calculation that can be done. All right? So this is just showing us how the reorder point thing works, where we start off with Q, and as we're consuming, when we get to that reorder point, that point right here, so our inventory level is going down, we place the order. Now if you look at this, you will get to your reorder point at this time, and this is where your inventory is supposed to arrive. So it means that this time must be your lead time right here, because that's the period you want that reorder point to cover. You want to make sure you have enough inventory that covers you and over that period, and then you will receive your order a little later on. All right? Simple example of reorder point. Demand 8,000 iPods. Now we should be talking about iPads. And 250-day booking year. So we look at the average daily demand is 8,000 divided by 250, which is 32 units per day. So if we know what our reorder point is in days, let's say our reorder point is 3 days, not reorder point, our lead time is 3 days. So 3 times 32 gives us 96 units is what we need to have on stock for us to be able to cover that period. All right. Now, let's take a look at the production order quantity model. So this model occurs in a production environment, hence the term production order quantity model, EOQ. And then what it is, as I mentioned earlier, is that you will consume the product that you're making. Here's an example I like to give. Let's say you are baking cookies for your child's Christmas fair coming up. Well, let's assume that you have an oven that could bake 100 cookies per hour. All right? 100 cookies per hour. But while you're baking, what if you're eating 5 or maybe 10 cookies per hour in that period? So then instead of accumulating at a rate of 100 cookies per hour, you're now accumulating at a rate of the 100 cookies minus your consumption, which is 10 cookies per hour. So you're now accumulating at a rate of 90 cookies per hour. So if we say let P be the production rate, which would be 100. Let U be the usage rate, which would be 10. So your actual accumulation rate is P minus U, 100 minus 10, which is 90 units per hour. So you'll find the model has a slightly different look to it. All right, and so here is the angle at which we're accumulating inventory. Okay, so instead of the 100 units per hour, we are now accumulating at a rate of 90 units per hour. So this is where you have the production and usage taking place right here. After we produce, let's say we produce for 1 hour, a time T, let's say that T was 1 hour. If we stop producing then we will start to consume. So I'm going to continue to eat my cookies at the rate of 10 per hour. So what happens now is that the 90 units that I've accumulated at the end of the production period, I am going to eat 10 per hour. So if I had 90 cookies, then it's going to take me 9 hours to finish eating all of them. And then the cycle continues again. Then I start to produce again. I'll produce at a rate of 90 because I'm producing at 100 minus 10 that I'm eating at the same time. And then 9 hours later, I continue the cycle. So that's what it looks like. It's a little different. So in other words, unlike the EOQ model, where the quantity is replenished instantaneously, so that's why we had a straight line, and then we went down this way. In this case, it's not produced instantaneously. It's produced at a rate, P. And so therefore, we will accumulate inventory. And not just at the rate P, but P minus U, right? So here's some of the parameters for this model. The same order quantity, same holding cost, but now we let T be the length of the production time in days. P be the daily production rate, and D the usage rate. Now I said U because U and usage make sense, but anyway, let's D be the daily demand rate, because we can calculate D by taking the annual demand and dividing by the number of days in a year. And so the annual holding cost is still pretty much the same, which is your average inventory level multiplied by your holding cost per unit. The average annual inventory is really the maximum inventory level divided by 2, and the maximum inventory level is really P minus D times T. Now you have PT minus T dt, but if we factor out the T, it would be P minus D times T. So if I go back to my example of I'm producing at a rate of 100 per hour, and then I'm using at a rate of 10 per hour, so it'd be 100 minus 10, which is 90, times however long I produce for. So if I produce for 3 hours, 3 times 90 is 270 units. So that's what this function would help us calculate. Essentially, what is the inventory level that we will accumulate? That inventory level will depend on how long we produce for, multiplied by the difference between the production and usage. Okay? And that's necessary to kind of put the model together. In the end, without going through it step by step, there are a number of calculations that we do. But in the end, and that I'll explain this a bit further on. However, in the end, we end up with a model that looks like this. This is the ordering cost. This is the holding cost, and the holding cost is a little different from just in the EOQ example we had H times Q multiplied by half, but now it has to be adjusted by the fact that we have consumption and usage at this. We have production and usage at the same time, and so therefore the holding cost is modified. And then we have the optimal order quantity, because remember that we said that when the setup costs and the holding costs are equal, that's when we get the optimum point. So if we equate those two functions and factor out Q, we will get the optimum order quantity to be 2ds, which is similar to what we had in the EOQ model. And notice we have H, but then the H, remember the H is now modified because our inventory holding cost is really this function right here. So not just H, but it's actually H times this piece right here. What it has, if you look at this, because D, the demand rate, is smaller than your production rate, then 1 minus D over P is a value that is smaller than 1. But what does that do? Let's just think about this for a second. So what that does, it actually reduces the effective holding rate. If we multiply this H by a value that is less than 1, it's making this denominator smaller than H. As a result, what would happen is your order quantity Q would be larger than your typical EOQ. If you use the same parameters for EOQ in this model, we'll actually get a higher order quantity. And the reason for that is because you are not, remember that your effective inventory level is not Q anymore. It's really the difference between what you would have produced Q, but remember you're using some of that at the same time. So your inventory that you accumulate is really your P minus D times your production time. So in other words, the difference between those two models is that because you accumulate less inventory under this model, you could actually produce more. All right, because you will use up some of that quantity at the same time, so that there's a difference between the EOQ model, which does not have simultaneous production and usage, compared to this model, where you could produce a larger quantity Q, because at the end of the day, that quantity Q is not your final inventory. Some of that Q would have been used, and so your final inventory, which is Imax, is now different from the initial quantity that you set out to produce. And that is not too difficult to demonstrate. All right. And I think if we look here, the cost parameters are the same. The cost parameters are the same. The production rate is 8 units per day. The demand rate is 4 units per day. And we can see now in this model, we actually are producing 283 units compared to the EOQ that we looked at earlier, which actually had an optimal order quantity of 200 units. Okay, so you see here that fraction of 4 over 8, which is a half, really reduced the effective value of the holding cost, which then allowed us to produce slightly higher optimum order quantity, 283. All right. Okay, this is just us expressing what we talked about a bit earlier. So D, the demand rate 4, was determined by the annual demand divided by the number of days in operation. And that's how we got 4. When the annual data are used, the equation becomes the equation that we've already seen, which is D2ds H, but H is actually modified by that ratio, by that fraction right here. Okay. Last but not least, let's just look at quickly quantity discount models. And quantity discount models, what happens is that it's not immediately obvious what the optimum order quantity is, and so we need to just go through a process that allows us to calculate what that optimum quantity is. So what we have is a situation where a supplier or manufacturer will offer different prices for different quantities. So if you order less than 500 units, you will get one price. Between 500 and 1,000, you get another price. Between 1,001 and 2,000, you get another price, etc., etc. It all depends. So the price breaks, we call that, will depend on the manufacturer of the product and all that sort of stuff. And so here's an example. 3 discount levels, 0 to 999, 1,000 to 199, and over 2,000. And there's no discount at this level, but there's a 4% discount and there's a 5% discount. So here's the initial price, and therefore these are the prices for the price breaks. So what happens is that we now need to figure out this process to take advantage of this. So what we would do is we would say, let's try to find a feasible EOQ. And by feasible EOQ, what we mean is that we use each cost factor and calculate the EOQ and see where those quantities fall. Depending on where they fall, one of them will be feasible. All right. So for each discount, calculate Q star. If Q for a discount does not qualify, that means you may get a quantity, but that quantity is not in the range to get that price. And that becomes clear as we do the example. Then that means it's not feasible. Okay. So what happens that is once we get the feasible EOQ, we will compare the cost of that value to ordering quantities higher than that to get the discounted prices. That becomes clear in the example. It's kind of hard to just explain it without looking at the picture. So let's just take a look at this example that we have here. So what will happen is this. We will say, okay, take the first cost curve, all right? So we will take the first cost curve and then we will calculate the EOQ based on the cost data for no discounted case. Well, in other words, so the first cost curve is basically the one that has no discounts. We will find a feasible EOQ. If we calculate this quantity here, it's in the range for that price, and so therefore that's feasible. What if we computed the EOQ for the second cost curve, which means for the second price break? All right. For that second price break, we will find our EOQ value here. But notice, if this is the economic order quantity for this price curve, but it falls in the range of 0 to 1,000, that means it's not feasible. If it fell in the range of 1,000 to 2,000, then it would have been feasible. But that EOQ, if you order that quantity, you're only going to get the non-discounted price. So that's why we say it's not feasible. Okay? And then if we would repeat that for this process, I'm sure you'll get the same problem where the EOQ for the third cost curve does not lie in the range up here. It lies either somewhere here or it lies in this range right here. So once we have found this feasible EOQ, which is here, now we'll say, okay, let's look at the total cost associated with this curve. But now to get into this price range, we will have to order a minimum quantity here, B. Let's order that minimum to get this price and see if the total cost is cheaper than the EOQ over here. And then we'll also say, but we could get a price break if we ordered this quantity right here and get this price. Now let's see if this total cost is cheaper than that one and cheaper than the cost associated with the EOQ. And whichever is cheapest, that's the one that we go with. So it's a simple process. So here's what we would do. So we take the very first price at $5. We calculate the EOQ, 2DS over H, but H in this case is given by the interest rate times the price. All right. So you see 700 cars, and that falls in the range of 0 to 999, right? 999. So that's feasible. Now let's do the second one. Oh, we find out that is 714. But guess what? That is not in the range of 1,000 to 1,999. So therefore, that is not feasible. Q3 at our third discounted price, at our third price, or the second discount, is 718. So these prices are not changing the quantities very much. So what you see here is that that is not feasible as well, because to get that price, you must order a minimum of 2,000. So the only feasible EOQ is Q1. So now what we're going to do is we will say, let us look at the cost of the 700 units, which is 25,700, and say, how did we get that? Well, you go back to the total cost curve. Total cost curve, we must determine what your annual product cost is. So the demand multiplied by the unit price will give you this. What's your annual ordering cost? Remember, your annual ordering cost is your demand divided by the quantity multiplied by the setup cost. And your holding cost is the average inventory, which is Q over 2 multiplied by the unit holding costs. When you add those three terms together, you will get 25,700. So now we say, let's try the next price level. But remember, to get into that price level, you must order a minimum of 1,000. Because the optimum order quantity was 714, you don't go ordering more than 1,000 to get into that cost curve, because anything more than 1,000 is going to be more expensive than 1,000. So you will basically just find the minimum necessary to get that price, 1,000 units. And we calculate what the total cost is, and we see is 24,725. And then we say, well, hang on a second. We have another possibility, which is to order 2,000 units and get this price right here. But you see what's happening. The more you order, your inventory costs are getting larger. Now you are reducing your ordering costs because you order in fewer and fewer times because your order quantity is larger. However, we must make sure that the inventory costs associated with keeping larger inventory levels is not greater than the discount that you're getting. Like you're getting just a discount of 5 cents per unit here, between from 480 to 475. But you better make sure that your unit holding cost is definitely smaller than that. If your cost for holding an additional unit is larger than that 5 cents, then you're not going to be profitable. So as you could see here, with this case, the cost is 24,822. While it's cheaper than this one, it is not cheaper than this price break right here. So in the end, this becomes our optimum quantity right here. Buy 1,000 units at 480, and that gives us the best value farm model. Okay. We're going to get into safety stock. And what is safety stock? So let's just pause and then do this in a separate video examining safety stock levels.